All right. So anyway, networking is really what we were talking about last class. But mainly home networking, because configuring your home network to keep your life good is going to be great. And I realized last class I was talking about how I've got 3 wireless networks at home. You said one for my guest network, one for my home, my standard, and one for my home automation stuff. And probably in the next few years, I'm going to add a fourth. One for my kids. So that way, when I want to turn internet off for them, I can press a button and it just disables internet to that one wireless network. Everything else in the house still has internet. So that is something that will be coming for me. Don't know how it's going to get set up yet, but it is on my list of things to magically do now. So, but anyway, yeah. So we talked about networking, and we talked about a good bit of networking. All right, we talked about MAC addresses. Anyone remember what that stands for? Yeah, I think so. Media access control. I always have to look that one up too. It makes you all feel any better. All right, but now, what is, I'm going to call it special in air quotes, about MAC addresses? They theoretically are what? Static, unique to every device. All right. So whether you're theoretically have your laptop here at HTC, or your laptop at home, or your laptop on Starbucks Wi-Fi, theoretically your MAC address is going to stay the same. Now, I did talk about last class how, for privacy purposes, companies have started creating randomized MAC addresses for different Wi-Fi names and things like that to reduce the capability of them to track you. Is really what it comes down to. Now, I did tell you I don't know how exactly the randomization works. If it's every time you connect to a Wi-Fi, or if you're on HTC Wi-Fi, you've got this MAC address. If you're on Starbucks, you've got that one. I don't know. I just know that that is something that they started to do. Now, to go along with MAC addresses, we have what? I guess I should put the screen up just so I'm not recording a prompt. We have that you guys can only see the top right corner of IP addresses. That's kind of nice that you were able to pull it off from that little bit. All right, so IP addresses. Now, this is really what we are using in the whole world for networking. We sometimes rely on MAC addresses, yes, and we will come back to that in a little bit. But for the most part, we actually are using IP addresses for our networking. Now, we did talk about how there are different subnets. So 20.24 /24 or 255.255.255.0 is like the kind of standard one you're going to use at your home. When you come to a place like HCC, let's just bring up my command window here. Do ipconfig /all, which I was going to get to today later, but oh, and this subnet mask is actually that exact same one, 255.255.255.0. So again, that specific one is being used for this exact computer right this moment. All right. Now, does that mean it's always going to be used that way? No. All right. But for the purposes of this, that's what we've got going on. All right. We also have IP version 4 and version 6, just as a quick reminder. So nothing too crazy going on there in the long run, in my opinion. Talk about the subnetting, which is what I've got going on here. And then this takes us to the wonderful world that I have of why do we have MAC and IP addresses? Why do we need 2 different ones? All right. And again, MAC addresses are hardware and they're encoded from the factory with this. All right. So we need to give it something to identify itself a little. But here up here on the screen, I've got a little demonstration going. Why do we like IP addresses? Well, we can easily group them. So when you show up here at SWIRT or HTC, they can say, okay, you're a student, and they can put you in the student pool. And when you go home, you can say, oh, I'm in the home pool. And it allows us to group devices. So even though the devices may not be local, like maybe not be in the same room in this case, right? We have laptops in here. So I've got, everywhere on campus, there's a laptop card. Not they're all over, but where they are, they're all connected to the same laptop card Wi-Fi, mobile card Wi-Fi. So they group all of those laptops together, even though they're not all locally. And by having IP addresses that we can assign to things allows us to do that type of thing. Right? So the other reason we have MAC addresses is, well, standards. This is something that we've been built on. Like, we have MAC addresses. The first addressing system that was used, what the case was. But this is how the standards have been built. So because we've used them so far, we're going to keep using them. All right. Let's So current protocols use allow for more flexibility in the future because we have those MAC addresses that we can rely on, and we can have these newer systems. So again, like IP version 6 is now coming out. Now, someone tell me, and I don't know how true this is. I've never actually Googled it, but IP version 6 is our public IP address. So someone was saying that basically every IP version 6 is public. And if we talked about how many freaking decillion, I think was the magic number, of IP version 6s there were, and I was like, yeah, each person can have like billions of IP addresses associated with them right now. It's obviously, it doesn't make sense. It isn't necessary for us to say, yeah, okay, we're going to have these public and private, other than for security. So, kind of an interesting little fact there. Again, don't know how true that is, but someone did tell me that at one point. All right. And what we have up here on the screen is data being forwarded from one point to another point. All right. So we have, data, an IP, and a MAC. So we're saying, hey, we're going to send this to this IP address, and then that changes the MAC address to the next one, changes the MAC address to the next one, so forth and so forth. Notice the IP address is staying the same. All right. So this IP address over this blue one that it's transmitting is actually the IP address of this server, and saying, hey, this is where I need to go. All right. So when this sends the packet, it says, hey, this is where it goes. It's my MAC address. This one goes, okay, I got you, and let me put my MAC address on it, so I send to the next hop. And then it keeps changing the MAC address as it's sending the hops. All right, notice the IP addresses. So again, another one of those reasons why we have MAC address is kind of important. We will come back to messaging like this in a few minutes, I believe. Now, we also have DNSs. All right, any of you guys heard of a DNS before, other than me talking last class? No? Okay. So, DNS is a dynamic naming system. All right. This is kind of like a phone book, as I have up on the screen. You all know the phone number to Papa John's. Now, but you know the website is papajohns.com. All right. So instead of you having to learn all the freaking IP addresses or phone numbers for Papa John's, you just know, I can go to papajohns.com, and it will take me to their website. All right. And this does a few things for us. Thing number one, it allows you to have things that are more easily memorable to you. Now, is a fourth three-digit number that hard to remember? 12 different numbers? No. All right. Y'all might not remember the days of having to know people's phone numbers. I do. All right. How many of you have your mother's phone number memorized? One of the four of you. All right. I have my mother's phone number. Okay. All right. Interesting random story, but when I was in college, my flip phone got wet. All right, so my the backlight went bad. Everything else about my phone worked perfectly fine, but the backlight on the phone didn't work anymore. So if someone called me, I could see who was calling, and I could dial a phone number, but I couldn't go to my address book. Backlight didn't. So I learned people's phone numbers for those 2 or 3 weeks. I had a phone with a backlight down. All right. And to that point today, it's like, okay, I still have some of these phone numbers memorized. Now, my mother's I knew way before I was in college, but still that sentiment is there. It's like, okay, when you're forced to memorize things or know things, you will, right? I have my wife's phone number memorized. How often do I put my wife's phone number? Not very often. But like when I go to the grocery store and they're like, what's your extra care number or whatever they're matching? It's like, oh, okay, wife's number. So it's just one of those things that like I've learned to memorize because I do use it frequently enough that I don't have to go look it up all the time. But anyway, the DNS is a phone book. All right. Google's is 8.8.8.8 or 8.8.4.4. Either one is the DNS for Google. All right. You also have 1.1.1.1.1. That's another one. That's the newer one. Right? And they claim that they are the fastest DNS provider. All right. And up here on the screen, they're showing you that their response time for a DNS query is 13.66 milliseconds. That is pretty freaking quick if you have milliseconds. Google's not too far behind, 22. OpenDNS, 23. VeriSign, 64. I don't know. All right. I've never heard of VeriSign other than this chart, and I looked them up. But anyway, these are all DNS providers. You get to pick your DNS provider if you want to. If you don't want to, your ISP will pick one for you. They're like, we're going to use this one or that one or those types of things. Right? So the DNS is the phone book. So it's like, okay, you're saying, hey, I need information about so-and-so. And let me just go ahead and throw this back up. That was exactly what I wanted. It's in the top screen. There we go. So if I'm going to do a quick command, so ping. Right? Ping is a command prompt command. Allows you to send a little bit of information to another computer. And basically you're trying to say, hey, are you there? All right, so in this case, I'm going to do Google. So 8.8.8.8, that's their DNS. And you can see here, we're getting a roughly, that was a long one. We got 6 millisecond time, 6 millisecond, then 40 milliseconds, then 7 milliseconds. Those are the response times. Just ping 1.1.1.1, just see if that is. I guess we're not going to ping 1.1.1.1. So 1.1, that company may block pings. You can actually set that up as a firewall. We don't respond to pings. I don't know why they want to, but you can set it up that way. I'm sure there is some security reason why you would want to do that. Let's go up to this one. Let's just do the 4.4 and see what that. In the long run, averaged a little bit better than the first one. All right. Oh, I've opened DNS. Anyway, so the phone book, you can pick your phone book, and it can be very helpful. HCC has their own DNS provider. Basically, they've got their own little cache, and that could be for multiple purposes. That could be that they just don't want to send all this extra traffic off campus, so they've bookmarked, the most popular sites that they see traffic for. And they've got them just stored locally, so that way when you go, hey, I need this information, they go, oh, here it is, and that way the request never has to leave campus. Right? It could be for the purposes of security. They don't want you going to certain websites. So instead of, when you say, I want to go to dicksportinggoods.com, they're like, that's a term that we don't like, so we're just going to block that. So when their DNS, their local DNS sees a term or something they don't like, they're just going to say, oh yeah, that IP address is 0.0.0.0, and then your website's like, and your web browser's like, all right, let's go to 0.0.0.0. It's like, can't be reached. Like, I know it's there, like it exists, I know. All right, so you can do things like that, and some places will do that. I used to do this, and I should really set it back up. Ad blocking via that. You have what they call a blacklist of websites that is all ads. Anytime you try to go to, yahooads.com or whatever it is, one of those websites that's trying to get an ad from Yahoo, they go, oh, sorry, that doesn't exist. And your DNS server will reply with that. It'll go, no, that doesn't exist, sorry. And it just, puts a gray box on your screen instead of an ad or something. Sometimes it's a gray box. Sometimes the box just disappears depending on how the website was coded. Right? So you can do DNS blocking for those types of situations. And again, most ads are safe and, they're there to sell you something. Some ads are questionable at best, right? So in that case, it is a safety thing. But anyway, we do have a DNS. If you ever see that, if you're ever required to type a DNS in, I would do 8.8.8 or 1.1.1.1, one of those two. You can use whatever DNS that you feel good with. And there are a lot of DNSs out there. You just find the one that you want to. Find the one that says that they're not going to sell your data and they're not going to do this, and hope for the best. That's actually what they're called for. So anyway, that is DNS. Any questions on that one? Not yet? Okay. All right, so TCP/IP. Perfect, say that I already did before, but this is your transmission control protocol / your internet protocol. Right? Now, this is where I'm going to lose you guys. I don't blame you. I get lost on stuff as well. I want to introduce you to this. I want you to know it exists, so that way when someone, your coworkers or something, says something about it, you at least have the faintest idea of what they're talking about. And sometimes it's very important. Sometimes it's not important at all. Right? But when we start getting to these obscure network protocols that you might run into, they're going to rely on different layers of the model. So we got to hit about it. All right, so this is the de facto global standard for the internet and for host-to-host layer implementation. And this is because of the popularity of it. So this is what they originally said, okay, this is how we're going to start building this up. So you can see that there's 3 different models kind of on the screen. We've got the OSI model, which is the de facto standard in the long run. All right, so you got the OSI, you got the ARPA model, and then you got TCP/IP position, where they actually sit. Now, anyone know what the ARPA model is? All right. Anyone know where the internet came from? Kinda. So the internet was actually developed as a government network. Right? They wanted a secure way to send information from point A to point B with redundancy. All right, so it's actually part of what is now a DARPA, Defense Against Research Project Agency, hence ARPA. I think it was the Advanced Research Project Agency. So that's where like the whole internet started, and they had multiple different, I think it was colleges and things like that. And the first, I think it was the first official logon attempt. They were trying to log on a computer from like Pittsburgh to California or something like that. The first like attempt, they were able to send one character before the network crashed. Kind of sad, but anyway, that's where the whole wonderful world of the internet came from. They went, they were networking these computers for government, military purposes, and then all of a sudden it kind of just skyrocketed to what we have today. So kind of interesting to look at that. So that's the ARPA model. That's what we have in the middle. So that's where we kind of started. Now the OSI model, which is on the left, that was developed in Europe by the International Organization for Standardization. Right? I almost guarantee you've all heard of this acronym before, ISO. Right? Haven't looked that one up. But anyway, that was where the OSI model came from. And you can kind of see that the ARPA model, they've said, okay, these top three layers are the application layer in the ARPA model, transport as service, network as internet, and then the network interface is data link and physical. So we have kind of actually like matched those up. Overall, ARPA is not really being used for our purposes anymore. We are all just looking at the OSI model. It's really what it comes down to. They both do have the same end goal of communication, or the OSI and the ARPA. All right. Now you do realize, or you hopefully will realize on the right-hand side here, that we don't have the first layer here, OSI. TCP/IP does not include OSI layer 1, or really layer 2 in this instance. All right, so it's purely our IP is the internet network layer, and TCP is the transport layer. All right, and so TCP is transmission, so transport. Makes sense in that aspect. All right. Now, IP is the internet layer. This is our network. And this is primarily responsible for routing packets from one host to another. So again, when we go back to that previous slide where we saw the packet going from one router to the next router to the next router, that's the IP protocol. That is getting the information from point A to point B. Right? That's really what it is focused on. This does use ARP, which is the Address Resolution Protocol. And this is used for the translation of an IP address to a hardware MAC address, such as required by Ethernet. Internet does require that MAC address. It's important, but we're not really using it on average every day. I mean, it's used, just we're not interacting with it. All right. We also have our reverse address resolution protocol, and this translates a hardware address to an IP. So ARP goes from IP to MAC, and RAP goes from MAC to IP. They go the opposite directions. All right. Now, as part of TCP, the higher level of transport layer, it's responsible for the data integrity. So IP is this whole goal there is to go from point A to point B. The TCP is like, is our data good? That what was supposed to be transmitted? Do we get everything? All those wonderful things. And we have two different ways of doing it. All right. The one that is mostly used is TCP. All right. That's that transmission control protocol. This is a connection-oriented protocol, which means it's all about a handshake. It's about me talking to Danielle and Danielle talking back to me. All right. We also have UDP, which is User Data Protocol. This one is not about a communication at all. This is about me lecturing you guys, me just spewing information and hoping that you all listening and gathering it, not playing on your phones or doing whatever else it is that you're doing in the class. So UDP is connectionless, so it's less reliable because I don't know if you're actually getting my data. I'm just sending it to you and praying that I get a response back from you with the data that I asked for. Not going, hey, you there? Good. Okay, here's the information. Did you get my information? All right, cool. Now, what are you sending me back? And then I'm going to go, yeah, I got your information back. So it's a lot of going back and forth. All right. However, the benefit here is by doing UDP, you have less overhead. There's less messages going back and forth. All right. So if a time sensitive thing, UDP is your better option because it's just me going, hey, my temperature is this. Hey, my temperature is this. Hey, my temperature is this. And if you need to, be super accurate with your timing on based on a temperature or whatever, UDP is going to be your option. TCP is not, because it's like, hey, buddy, you there? Yeah. Oh, here's my temperature. And by that point, the temperature changed already. So there is definitely a benefit to that UDP, even though technically it is less reliable because you don't know if your data is actually getting. So there's a little bit of a give and take going on. All right. So anyway, the OSI model, we will we will be coming back to this. This is just your first little introduction to that. All right. So here we have a little TCP/IP thing going on. You can just go back and forth. All right. So that will come over and then it comes back. And again, notice that we do have like the OSI-ish model on here, right? If we come back, application TCP/IP network application. And this is kind of like a combination of them all. But anyway, you can see that information is being sent to that and coming right back. All right. So this would be a PLC on the right, in case you didn't know. Programmable logic controller. Over here on the left, we have a VFD, or a variable frequency drive. All right. So this would be the PLC saying, hey, VFD, spin the motor at this speed. And the VFD is going, yes, sir, and send that information back. All right. And it's just constantly going back and forth. All right. Hey, now this speed. All right, I got you. All right. If we look at the UDP, now we have a PLC and a sensor. We got our PLC, now we have a sensor over here. Notice everything is going this direction. There's nothing going back. So this is just that sensor saying, for those who are interested, the flow rate's this. That's what's going on here. Now it is directing it to a specific address, so it's like, hey, PLC, the flow rate's this, but it's still just broadcasting it on the network. It doesn't know if it's getting it back. In this case, it doesn't care. It's a dumb sensor. All its job to do is to send its information out. Its job is not to detect whether it's actually there or not. Now the PLC will hopefully have some fault set up in place. Like if I haven't got a new sensor in 30 seconds or 10 seconds, whatever the magic time is, to like throw a red flag up saying, error, problem going on here. I don't have a flow rate. But hopefully that's what's going on. All right. Any question, TCP UPD? I think they overall make sense, especially if you just think about it as handshake for one, broadcast for the other. To me, that's the important aspect. I'm sure there's a lot more importance to really diving down into these, but for me, those are the two important things. All right, so here we have what would qualify as a standard network. All right, so when we were talking about serial, all right, we had that like standard packet, right, of information that got sent. What got sent with serial? What was the first thing that got sent? Yep, so we had a start bit. We had start, and then what did we send? Then we sent data of some sort. And then what did we send? What? Parity, if we included it. And then what? End or stop. So remember, it would be HN1, right? We normally send. All right. So here is roughly the same idea. There is a very specific, this is the information that we need to be sending. All right. So we have our local network frame. That's what we got showing here. So we have our header. We have our, basically, this would be our start. This would be our stop in the long run. All right. Now we do have our data here, but there's more headers going on. We've got, because this is on a network, right? With serial, we have two devices talking back and forth to each other. If I'm broadcasting information on the serial port, the other device is probably wanting it. It's not like I'm going, hey, Dylan, you there? And I'm talking to Braden or someone else. It's like, no, it's on the serial port. It's like, this is who I'm talking to. I don't have any other options. Now, when we get into the world of networking, obviously, there are a lot of other options going on, right? Talked about there could be thousands of devices on a network, especially if we take an HEC campus. I'd actually love to find out from IT how many different IP addresses they have, on the network in a given day. How many different devices? And if we just look at like security cameras alone, I wouldn't be surprised if there's 1,000 security cameras. If you think about like on the STEM building, it's like, okay, on the third floor alone, there's 1, 2, 3. I think I can count 5 at least just on the 3rd floor. And then you go down a floor, there's probably 5 more, and down a floor, 5 more. Like, oh, this. And then you start thinking at in lab spaces, like across the hall here in the CNC lab, they've got a camera in the lab as well. And here we don't have a camera, teaching space. I don't know why it matters, but that's their definition. That's where they draw their lines. All right, but it's like, oh, there's security cameras everywhere. Probably 1,000 is a little overkill, but still, I wouldn't be surprised if there were a few hundred minimum security cameras on campus. Let alone, like, again, everyone who has a cell phone on campus. Oh, and tablet and laptop and this and that. Number discussed. All right. So that IP header, that's going to be important. All right. Now, my notes do say that the header and the trailer, these will change depending on the network type that we're using. Right. So if you're using Ethernet, or if you're doing a modem or fiber optic or something like that, those may be changing depending on that network type. So just something to take into account. The IP datagram is not touched unless the network requires smaller packets. So when we are sending information from here to the internet, all right, this IP datagram right here in the center, the IP header, the UDP, and the application data, that does not get changed. The header and trailer, that may change. But this core doesn't change unless you all of a sudden are sending it over a connection that says, whoa, that's too many bits. Right? Because if you have your IP header, and that's a version 4, that's 32, and then you've got your UDP TBC, I don't know how many that is, and then this, I have this all on another slide. But it's like, okay, you're sending 128 bytes or bits or whatever. It's like, oh, well, ours only handles 64. So we can't send this as one giant packet. We have to say, okay, we've got to break this up into little, kind of like trying to mail a car. You got to have a rather large truck to move the car around. It's like, oh, you need tires? Yeah, I can get you tires in the back of my pickup truck. Oh, you need a motor? I can put that in the back of my pickup truck. And break it down into smaller pieces and reassemble it after the fact. So you could do things like that. But anyway, that diagram overall not really touched. And when it is touched and manipulated in a way that, like the IP header and things, there are always groups, so that information is always there. So here we should have, here we go, the IP datagram. All right. So there is a lot going on in this. I'm sure you're all looking at this like, WTF, man. Right? I mean, we've got 32 bits wide, and there's 1, 2, 3, 4, 5, 6 tall, or up to 6 tall, maybe. All right, because we do have options and padding at the bottom. All right, 32 bits, 6 tall. That's what, 180 something? 30 times 180, 192. 192 bits is what we're talking about here. All right. So the IP portion of the TCP/IP, this is the equivalent of the postal service. It is responsible for delivery of the packets. Make sure those packets get there. That is its whole job. All right. It forwards and routes the datagrams based on the IP address attached to the datagrams. So this is just how mail would get to your house. If someone in Massachusetts decides, I'm going to send a piece of mail to you, they look at the mail and they go, okay, it's heading this direction, we'll put it on this truck. And they get to the next station, okay, it's heading this direction, we'll put it on that truck. And they just keep moving trucks until it finally gets delivered to your house. Same thing's going on here. All right. If we do need to fragment that datagram, IP is also who's going to be doing it. So kind of keep it the same. Ethernet can handle 1,500 bytes. But some of this stuff can only handle 576 bytes. So again, something to keep in mind when we're talking about the information we're transmitting. Just scroll there. Ethernet, so IP is a minimum of 5 32-bit words, at a minimum. So I had 6 written. Where'd my pen go? I had 6, again, we said, this one's options. So at a minimum, we have 5. All right, but it could be more. All right. So up here at the top, version, this is the version IP being used. Now you may be going, isn't there just one version? Is there ever just one version? Unless you are the person who made something, there's probably never just one, right? Like, oh yeah, I'm going to write some program, right? And I write my programs at home. I do not have one version. Every day I have a version. Because when I write a program and the next day I come to it and I start editing it, I save it as a new file. So when I completely and utterly screw it up and it doesn't work at all at the end of the day, I've only lost 24 hours worth. All right, because I can just open up the previous days and go, okay, this one is working. What did I change? What was I trying to accomplish? Those types of things. So versions going to be important. All right, you have the IHL, which is your internal internet header length. All right, we have our type of service, and this informs the network about the quality of service. Now, when you send information from point A to point B on the network, it's kind of like, which highway do you want to take? You want to drive again from here to Massachusetts. How are you going to drive? You can take all the back roads. You're going to take the highways. You're going to jump on the turnpike and pay. You know, which option is it that you want to take? Right? And the same thing goes for the internet. Your ISP has deals with all its other ISP and all the other like local, network links back the backbones to get information, and they're paying them based on how much data they're sending through. And depending on the importance, we're going to go different routes. So we have, for types of service, we have minimum delay. So I want it there ASAP. We have, I have a lot of data I'm sending, so I'm going to send it this way. You have max reliability. I don't care what it costs. I need my data to get there. It takes a little longer, that's fine, but make sure it gets there the first time. And then you have also the cheapest options. All right? It's kind of interesting to me. It is cheaper. If you have an 8 terabyte hard drive full of data, like Google, it is cheaper for them to physically put that in like a post office, like a box, and mail it, than it is for them to send it via the internet. And depending on the situation, it's also quicker. Like, I can do next day delivery. I can have this entire, shipping container full of hard drives that's petabytes of storage. I can have someone get in a truck, drive it, 36 hours down the road. It'll be there in 2 days. Great. Or you could go, I could upload to the internet. My internet speed's only 2 gigabits, so it's going to take ages to upload everything to get over there. Plus, it's going to cost a lot. So one of those things you have to think about. When I was doing stuff with drones, which I still do stuff with, we have drone classes. But one of the companies I was talking with, they said, they physically mail their media instead of uploading it to the internet. Because of that exact thing. Like, they go out to some farm 2 states away and they're staying in hotels for the time. Hotels, as you all know probably, don't have great internet connection. So for them to send gigabytes of information of all these pictures they've taken up to the internet, it's like, it's going to take 4 days to upload everything. Or we can throw it in a post office envelope, mail it back home, next day delivery for $50 or whatever the cost is. And they can upload it and start processing the data tomorrow. Because it's direct connection to the server. It's like, it's just over the network. Now we've got a 10 gig network connection instead of 2 megabits. All right, so huge difference in quality of service. So it's kind of something that you want to kind of keep in the back of your mind when you're transmitting lots of data. Sometimes it's easier just to freaking pass a flash drive around and you guys copying stuff off of that. Next, we have our identifier, which identifies each datagram sent by host. So this is like your tracking. Did that get there? Yep. Okay. We've got our fragment offset over here on the right. That's used if the case of fragmentation, used to reassemble data. So if we do have to fragment it, okay, this is packet 1, 2, 3, 4, 5, of that data that we're reassembling. You've got TTL, which is your time to live. Now this one is actually I'm not clicking, I'm trying to scroll. This one is very important because this is saying, okay, my datagram, it's getting bounced from router to router to router to router all over the internet trying to get home. And you'd think, okay, it's going to go from here to the ISP and then back home. That's how this data should travel. And then that link between here and my ISP at home is down. So it's like, okay, we're going to send it down to Illinois, or not Illinois, West Virginia. All right, and then West Virginia is going to send it back, back up. And then that link is down. Then it sends it back up, and then that link's down, or full, or whatever the case. Okay, now what? Well, all of a sudden it goes, I've been transitioning around for 5 minutes. I'm done. Uncle, data never got sent. Try resending it. Hopefully 5 minutes is not how long your packets are living for, but maybe. All right, and hopefully at that point your computer's going, I never got a response. Let's send my information out again. And now this time that link isn't broken, it's fixed. Right there, I'm done. All right, that's kind of like why we looked at those pings and we saw 7 milliseconds and 40 milliseconds. Well, the one route was blocked, capacity, whatever. So it went, okay, we're going to reroute you this way and send you around. So it took longer. Data still got there though. All right, now we go to protocol. We have, if we're going to use TCP, that would be a number 6 there. If we're using UDP, that'd be 17. There's also ICMP, which we haven't talked about. That's number 1. All right. And then you've got checksum for error checking of the header only. All right. So that checksum that is the checking for errors is only for all of the information that we've just talked about. It is not at all for any of this stuff down here. This checksum only checks all of that stuff. I find to be kind of interesting. All right. So that is like your datagram of it. So a lot more going on here than serial, right? It's like, oh, here are my first 8 bytes or bits. Here's my next 8 bits. Here's my next 8 bits. You know, put it back together. Have a nice day. Kind of crazy in that aspect. All right. Now, one of the ways we share information. How do you share your internet? Right? You send out your packet to Amazon. Your brother's next to you send out a packet to eBay. How does it know to get you your Amazon packet and his eBay packet? Right? And there's a lot of different ways they can. But again, that whole MAC address, that is going to be an important aspect of this. They could do it based on ports and things like that. So when we go into the world of ports, all right, anyone know what a port is for your network? Give me your best description. Okay. So, best description I had for a port. It's a hole in the wall in your house that leads to one specific thing. Right? So, in this instance, the port that you guys are using the most is either 81 or where is the other one? There we go, 443 for secure. All right. So what I mean here is, imagine you have a room, a wall full of windows, and you want to talk to HTC's web server that has their website on it. You go to a specific window in it, and all the information that goes to HTC's web server goes through that one little window. And then you're like, oh, if I need to go to the printers, well, that printers is on a different port, so that's a different window. So all the information that's going to the printers is going over here to this window. All right, so it's just a whole bunch of holes or windows on a wall. Right? And these are the default ones. Does that mean these are the ones that have to be used? No. All right? You can pick a different port to cause problems, per se. I'll call it. All right. So in this instance, HTTP, default support 80. All right. Now, most websites aren't using HTTP anymore. They're using HTTPS. All right. So they're now using port 443. All right. So most web traffic is going through a different window than it used to. And the whole point of it being secure is so your data doesn't get stolen, right? It's like, okay, you're logging into a website. If you just log into an HTTP website, in the information you're sending, you're like, hey, my password's this. Just right out there, all right? And if you think about it, your data is being sent from your computer. Maybe you're on a secure Wi-Fi. That's great, right? But then it goes out of your house. Are all the lines between your house and that server secure? Not necessarily. All right, your ISP could be snooping. You're like, oh, we're gonna read all this data, we're gonna log all this data, and we come back to it. All right, so just because at your home level it's secure, which you really should have everything secured as much as possible, doesn't mean it's actually being secure from that point on. Right? Where HTTP is encrypting that data that's being. So you encrypt it, and then the other side has to decrypt it. Here, only those two sides have that handshake of how to decrypt things. That's why we like the secure. All right. But anyway, so these are the most used one. Some that are used probably rather frequently. You've got 22 for your SSH remote shell. So if you're trying to log into a computer remotely for a command line mainly used for Linux, you're going to go with port 222. My students in my Linux class right now are actually logging to 2220. And again, it was just that company said, okay, we're going to change the port up. Perfectly fine. Yeah, DNSs, that's traditionally port 53. What other really ones? For you guys, those are probably the most important ones. For your DHCP stuff going on. All right. Anyway, these are the most used stuff when it comes to. All right. Ports are going to be important. Now, the other thing I'll say is, if you set up something, you're setting up the server. Hopefully, you're not the person setting up the server at your company that you're working for the wonderful electrical engineering. But if you are, and you're like, okay, why can nobody access my server I just set up? Because IT has the port blocked. Or the firewall on your computer has that port blocked. So it's like, yeah, I'm getting traffic, but I'm not letting it through. All right. Whole point of a firewall is to go, is stuff allowed to come through this hole? Go, yes, or oh. All right. All right. So that's the whole point of firewalls. Keep the traffic that's not supposed to get through going through. So, all right. That finishes up my whole wonderful world of TCP, IP, wonderful networking stuff. Major questions for me? All right. Let me go ahead and stop the recording now.